In this video, I'm going to cover part 3 of the physical pendulum experiment, EX-5518. In this portion, we're going to be measuring the moment of inertia at the center of mass for the irregular shape. To do this, you're going to need a couple things. First of all, some scissors. Then you're going to need some twine, and then also a mass and hanger set, which I'm using right here. And then we have the rotary motion sensor with the super pulley attached here at the end. So when setting this up, let me share my screen here. So when you're setting this up, go ahead and open the capstone file for this experiment. And what you're going to do is, taking the pulley, you'll see there's a black thread right here. And you'll notice that it is tied into the hole right here. There's a little hole right here. And just tie a knot to the back of that. So now you have some thread attached. Now we're going to go ahead and put that back on the rotary motion sensor. All right. Make sure our line is out. Now we're going to mount the rotary motion sensor on the rod stand here. I used a shorter rod stand for this video just because it's easier to show. It's not off the screen. So once you mount that on there, I have this suspended so that it's over the edge of the table so it can just keep falling. And go ahead and attach the irregular shape. We can go ahead and start winding up the spindle. All right. Oops, jumped off there. There we go. All right. So let's make sure everything is connected correctly. Let's go into hardware setup here and go to the rotary motion sensor. I did this earlier, so I need to change the sign so the graph is positive. Doesn't really matter. All we're trying to collect is the slope data. And then we need to change the linear accessory to the large pulley groove since we're on the largest part of the pulley. This part right here. And we'll hit OK. After that, we'll close this. And let's just increase the sample rate just a little bit so we'll get some better data. And what we're going to do here is click record and then release the irregular shape and let it rotate about the center. Let's change this to velocity. We're going to hit record and we'll let it go and stop. So now, because we're measuring velocity against time, the slope of this line in the linear region will be an acceleration value. So that's the value we're trying to get. So we're going to go ahead and let's expand this out. Let's just get rid of the legend there. Expand this out a little bit more. There we go. Going to use our area select tool just to select the area for which we want to get a linear fit. And then we're going to apply a linear fit here. So 0.781 is our linear acceleration value. And so we're going to write that down here. So with this, we can now calculate the force that we've applied by doing this. The force is equal to the mass times the difference between the acceleration due to gravity and the acceleration that we just experienced. And so we'll plug that value in right there. And after that, we can calculate that value. Make this a little bit smaller here. There we go. So we can calculate that out. If we do, let's see, 9.8 minus 0.781 is 9.09 times 0.01. So we have 0.09019 newtons. Oops. And then we can take that value and plug it into this formula. It states that the rotational inertia is equal to the radius times the force divided by the angular acceleration. In this case, the radius is 0.024, and the force is what we just found there, 0.9019. And then divided by the angular acceleration, which we can get by going back to this. We can do the same thing here. And just apply a curve fit to this region. Linear. 32.6. And then if we go ahead and calculate these values out, so we have 0.024 times 0.09, 0.019, and then divided by 32.6 gives us, there we go, 0.0000663 kilograms per meter squared. That's the rotational inertia. And we're comparing that to the value that we found in the first video, which came out to 0.000593. And we want to find the percent difference between these two values. So if we do that, and we'll do the math here. Oops. Divided by times 100%. So we have about a 10.5% difference. That also tells us we'll have some accuracy when using the period, but measuring directly will still be best. It's also worth noting that the value we obtained here is actually going to be a little bit higher because we didn't account for the mass of the pulley as well as the spindle on the rotary motion sensor, which you can find by removing the irregular shape and doing the same procedure without it, and then find the moment of inertia of just the pulley and the rotary motion sensor and subtract that from this value right here to get the real value. And that is completing part 3 of the physical pendulum experiment.